interact with molecules of sample, then the electrons present in different quantized energy level, then the electrons present in different quantized electronics energy level, they will undergo transition. So when the electron will move from ground state to any excited state, so the molecule is in excited state, and again we know that the lifetime of electrons in the excited state is very short. So these relax back to the ground state using different processes. That means again the electron will come back from the excited state to ground state by different processes. In some of the processes, so now we'll discuss what are the different processes for the relaxation of molecules. In some of the processes, the absorbed energy is given up as heat to the surroundings, and in some it is emitted as radiation. So when such a relaxation is accompanied by emission of radiation, it is called a luminescence. That means the electrons in the excited state have very short time, short life. So again they will come back to the ground state by emitting energy. So they will emit energy in the form of heat, or they will emit energy in the form of radiation. So if the relaxation process is accompanied by emission of energy in the form of radiation, that process is called a luminescence. And there are two types of luminescence phenomena are there. The first one is fluorescence and the next one is phosphorescence. And fluorescence is the emission of the visible light by substances that has absorbed light of different wavelength. So the emitted photon has a longer wavelength, and phosphorescence is related to the fluorescence in emitting a photon. However, the phosphorescent material does not immediately re-emit the radiation of it absorbed. That means if the molecule come back to the ground state by emitting electromagnetic radiation, or by emitting light, by emitting visible light, immediately that process is called fluorescence. And if the molecule will emit visible light after some times, not immediately, that will so re-emit the radiation it absorbs, that process is known as phosphorescence. As the excitation molecule is due to the absorption of a photon, these type of luminescence are called phosphorescence. Now coming to chemiluminescence. Chemiluminescence, another phenomenon that falls under this category of luminescence. This refers to emission of radiation during a chemical reaction. However, in such cases, the excited state is not a result of absorption of electromagnetic radiation, so rather that the excitation state will achieve by chemical reaction. And here one example is there, the oxidation of luminol. So this is luminol, so this molecule is luminol. So if luminol will undergo oxidation by any process in an alkaline, so the process is that, so if the oxidation of luminol takes place in an alkaline solution, that is an example of chemiluminescence. And the method is like that: an aqueous solution of luminol is, is oxidized by solution of sodium chlorate, that is commercially available bleaching powder. So the luminol will undergo oxidation by chemical process that is known as the bleaching powder. When that will react with commercially available bleaching powder, then the luminol will undergo oxidation and gives out blue glow without increase in temperature. Now the luminol is oxidized to aminophthalate ion. So when the luminol so react with commercially available bleaching powder, that will undergo oxidation to form aminophthalate ion. Now the aminophthalate ion will produce blue glow, and the luminol is oxidized into amino phthalate ion, which is produced in an excited state and emit blue light on dropping the ground state. And the reaction, so here this is the reaction, and this process is known as chemilumination. So this is another type of luminescence phenomenon, but in this type of luminescence, the molecule will not go to excited state by irradiation with electromagnetic radiation. So rather than it will go to the excited state due to chemical reaction. So the process involved in the excitation by radiation and radiative emission can be understood by a very common, well-known diagram that is known as Jablonski diagram. So this is one long question. So now we'll discuss what is Jablonski diagram. So the Jablonski diagram gives a representation of a ground and different excited electronic state of a molecule and the process and the different processes associated with absorption or emission of energy. So this is a typical Jablonski diagram. So you have to draw this diagram. So now we'll discuss what are the different phenomenon associated with absorption or emission of light that is explained in this Jablonski diagram. So a typical Jablonski diagram is given in this figure. You can see in this figure, you can see, so these are known as the ground state. So the ground state of any molecules are designated as S0 or S0, and this is the first excited state S1. These are the second excited state S2. So why these are called S1, S2, S0? Because these are singlet state. Singlet state means in this state the two electrons present are in pair form. The two electrons present that will be in pair. So the total spin equals to plus half minus half, that is equals to 0. And hence the multiplicity we know that 2s plus 1 that is equals to 1. So that's why these states are called singlet state. And here this is an triplet excited state. So in the triplet excited state, the two electrons are in parallel spin, and hence the total spin of will become plus half, so that will become 1. And if you calculate the multiplicity, that will become 2 into 1 plus 1, that will become 3. That's why that's called triplet excited state. A set of lines at the bottom of the figure represent the ground state, and one in the upper portion indicate the excited electronic state. So these lines are called ground state, and the upper portion, all the lines are called excited state. To begin, the molecule is in electronic ground state. In this state, the molecular orbitals are accompanied by two electrons, and again we know that according to the Pauli's exclusion principle, the spins of the two electrons in the same orbital must be antiparallel. So this implies that the total spin S of the molecule in the ground state will become plus half plus minus half, that will become 0, and the energy state is called singlet state, that is labeled as S0 or S0. So why it is called singlet state? Because if the molecules present in the two electrons present in the ground state will be antiparallel to one another, and hence the total spin will become plus half minus half plus minus half, that is equals to 0. So total spin will be 0, and according to the formula of the multiplicity, that is 2s plus 1. So 2 into 0 plus 1, that is equals to 1. So that's why this state is called singlet state. So this is the reason this state is called a singlet state. Now coming to singlet excited state. So in the singlet excited state, one electron in upward spin and another electron in downward spin. So the total spin also 0. and the multiplicity will become 1. That's why that is called singlet excited state, S1. And in excited triplet state, both the electrons are in upward spin, and hence the total spin will become plus half, that is equals to 1, and the multiplicity will become 2s plus 1, that is equals to 3. That's why that is called a triplet excited state. So the energy of the two excited spin states are also different to the difference in the interaction between the electrons. So the energy of the triplet state usually being lower than the singlet state. Then the Jablonski diagram, then in the Jablonski diagram, the two excited singlet states, that is S1 and S2, and a triplet state are shown. So here, so these are the two excited singlet states. So here these are the two excited. So this is first excited singlet state S1. This is second excited singlet state S2, and this is one excited triplet state T1. So in the Jablonski diagram, only these three steps are there. Now coming to, so in the Jablonski diagram, two excited states S1 and S2 and a triplet state T1 are shown. So the absorption and emission of radiation leads to the activation and deactivation processes. So if the molecule will undergo absorption, then that will undergo the process of activation, and if that will emit energy, that is called a deactivation process. So absorption of energy leads to activation, emission of energy leads to deactivation. Now let us learn about the way of activation and deactivation processes. So here we will discuss what are the different activation and deactivation processes. The absorption of photons with suitable energy causes the molecule to get excited from ground state to one of the excited state. This process is called excitation or activation, and the excitation activation is governed by the Frank-Condon principle. Now, according to this principle, the electronic transition takes place so fast, it is around the time taken for the electronic transition is around 10 to the power minus 15 second. So the transition takes place so fast that the molecule does not get an opportunity to execute vibration. So when the electrons are excited, the internuclear distance does not change. The basis of the principle is that the nuclei is very massive as compared to the electrons and therefore move very slowly. Now, the implication of Frank-Condon principle is that the transition from the ground state to the excited state can be represented by vertical arrows in the Jablonski diagram. So these are the transitions from the ground state to excited state. So these are vertical arrows. You can see these vertical arrows are shown in Jablonski diagram. So these are the excited. These are excitation of electrons from the ground state to the S1 state, and similarly, these arrows show excitation of electrons from the ground state to the S2 state. So the electronic transition takes place from the state of lower vibrational energy of an electronic ground state to any of the vibrational energy levels of the excited electronic state are shown in vertical upward arrows in the diagram. And again, you should know that. So these are the different vibrational levels of ground electronic state. And again, these are the different vibrational levels of fast excited state electronic state. These are the different vibrational energy levels of second excited state electronic state. So when electromagnetic radiations will fall on the sample, the fall on the molecule, the electrons from the ground state, and again from the ground vibrational energy level, ground electronic state and ground vibrational energy level, they will excite into the ground vibrational energy level of fast excited electronic state. Similarly, they may excite to the fast excited state ground first excited state vibrational energy level of S1 state, or third or second excited vibrational energy level of S1 state, and so on. So the excited state is achieved. The excited state achieved would depend upon the energy of the photon absorbed by the molecules. So the diagram, in the diagram, two excited states S1 and S2 have been shown. These are obtained by absorption of radiation in the region of wavelength lambda 1 and lambda 2 respectively. Once the molecule gets excited by absorption of radiation, it does not stay excited indefinitely. So a number of processes bring back to the ground state, and that process is known as deactivation. So as soon as the molecule reach the excited state, immediately they will come back to the ground state by different processes, and these different processes are called as deactivation. Now let us discuss what are the different processes of deactivation. So the deactivation takes place generally two different processes. First one is non-radiative deactivation, and the second one is radiative deactivation. So first we will discuss what is non-radiative deactivation. So during the non-radiative deactivation, that means the molecule will come, the electrons present in the molecule will come back to the ground state from the excited state by emitting heat, not by emitting light. So they will come back to the ground state by emitting heat. That's why these processes are called non-radiative deactivation. But in case of radiative deactivations, the electrons will come back from the excited state to the ground state by emitting light. So that's why that is called radiative deactivation. But here first we will discuss what is non-radiative deactivation. So these deactivation mechanisms are not accompanied by any radiative loss. So three different non-radiative deactivation processes are there. So the first one is vibrational relaxation. So in the higher vibrational levels of an excited state, the molecules rapidly lose its excess of vibrational energy by collision with other molecules and fall to the lowest vibrational energy level to the excited state. In this non-radiative mode of relaxation, this type of non-radiative mode of relaxation is called vibrational relaxation. That means in the vibrational relaxation process, the molecule will come back to the ground state by collision with other molecules. And during the collision, so the excited molecule will lose energy in the due to vibration. So in this principle, the non-radiative or radiation-less deactivation may also lead to the relaxation of S1 to S0 state. However, such relaxation is quite slow. So that means molecule from the S1 state may come back to the S0 state by non-radiative deactivation. That is called vibrational relaxation. And another one is internal but the process is quite slow process. Another one is internal conversion, or that is called IC. Once the molecule that are excited to an electronic state, that is called S2, which is higher than the S1 state. S1 state is first excited electronic state, S2 is the second excited electronic state, and similarly that may be S3, that is the third excited electronic state. So during the process of internal conversion, the molecules that are excited to an electronic level which is more than S1, that may be S2 or S3 state, reach the vibrational ground state in the electronic level. This can pass to a higher vibrational energy level of lower excited state which has the same energy. This process is called internal conversion or IC. You can see the process of IC. So during the process of IC, see, so this is the blue color line, that is so internal conversion IC. So in the internal conversion IC, the molecule from the S2 excited state come back to the higher vibrational energy level of S1 excited state. So the molecule will come back from the ground state vibrational level of S2 excited state to the third excited state vibrational energy level of S1 state. So these processes are called internal conversion. These are also non-radiative transition. So the molecule can continue to lose energy in this state in a non-radiative way, and that is also one type of vibrational relaxation until it reaches the lowest vibrational level in the excited state. So that means by the process of IC, the molecules will reach lowest vibrational energy level of the excited state. Now coming to another type of relaxation process, that is called inter-system crossing (ISC). The first one is vibrational relaxation, then IC, then inter-system crossing (ISC). So in the rare occasions, the molecules in the vibrational state of a singlet excited state may cross over to a vibrational levels of the triplet state if two have the same energy. This process is called inter-system crossing or IC. So this spin exchange mechanism may also lead, though very rarely, and the crossing over from a triplet state to a singlet state. So you can see in the ISC process, so this is inter-system crossing. So in the inter-system crossing, the molecules will come back from the S1 vibrational energy level to ground state vibrational energy level from of S1 state to the second excited state energy level of T1 state. So that is called intersystem crossing. That means if the molecule will undergo transition from S2 to S1, that is called IC, internal conversion, and if the molecule will undergo conversion from S1 to T1, that is called intersystem crossing ISC. So all these are so all these processes leading to decrease of energy without any type of radiation. Now coming to the radiative deactivation. So when the molecules in the excited state, that is S1 state, relax down to the lowest vibrational level, it may emit a photon and come down to the S naught state. This process is called fluorescence, and it will takes about 10 to the power 9 minus 9 second. That means now the molecule will present in the fast excited singlet state in the ground vibrational energy level of fast excited singlet state, that is ground vibrational energy level of S1 state. So from the ground vibrational energy level of S1 state, if they will come back to the different vibrational energy levels of ground state, electron state or S0 state, so this process are called fluorescence. And the time taken for the process of fluorescence is around 10 to the power minus 9 second after excitation. So the time taken for internal conversion and ISC is around 10 to the power minus 15 second after excitation. But for fluorescence, the time taken is around 10 to the power minus 9 second. And that is one type of radiative process. That means when the molecules come back from the ground vibrational energy level of S1 state to any vibrational energy level of S0 state, that process is called fluorescence, and that will take place at about 10 to the power minus 9 second. And similarly, another radiative relaxation process can arise from the excited molecules that are crossed over to the triplet excited state by intersystem crossing has relaxed to the vibrational ground state in the triplet excited state. In such a case, the molecule emit a photon and come down to the vibrational mode of the electronic ground state S0. This phenomenon is called phosphorescence. That means in the process of phosphorescence, the molecule will come back from the ground vibrational energy level of T1 state to any vibrational energy level of S1 state. So these processes are called phosphorescence. As the transition from a triplet state to a singlet state is theoretically forbidden, it does not take place rapidly. So that's why this is a slow process. Thus, while fluorescence takes place, while fluorescence, because we know that the transition from the triplet state to the singlet state is forbidden. So, for this type of transition, the electrons in the triplet state, first they will convert into the singlet state, and after that they will undergo transition from the triplet to the singlet state. So that's why for the fluorescence, the time taken is around 10 to the power minus 9 to 10 to the power minus 6 second. But the transition from an excited triplet state to the, that means the transition from the T1 state to the T0 state, that process is called phosphorescence. It will require at least 10 to the power 4 second and may take as long 10 to the power 2 second. That means from 10 to the power minus 4 second to 100 second. Since the fluorescence emission takes place only after the excited molecule has relaxed to the vibrational ground state of the S1 state, that is after having lost part of its energy, the energy of the emitted radiation is lower than that of the excited radiation. So that means for the fluorescence, the molecule will come back from the vibrational, from the ground state vibrational energy state to the S1 state. So that means before the process of fluorescence, the molecule already lost some amount of energy due to internal conversion. So that's why the wavelength of the fluorescence will be a longer wavelength that of the excitation wavelength. So this means that the wavelength of fluorescence emission would be a greater than that of the excited wavelength. Further, since the energy of the triplet excited state of the molecule is lower than that associated with the singlet state, the transition to the ground state are associated with emission of light still lower energy. As a consequence, phosphorescence occurs at still longer wavelength than that of the fluorescence. Now, in this figure, you can see, so this is the wavelength of the excitation of the molecule, and this is the wavelength fluorescence having longer wavelength and lesser energy, and this is the wavelength for phosphorescence. So the excited molecule when reach a triplet state spend relatively long time in the state. Since they are in the triplet state for a long time, they can lose their energy by means of other than by emission of photon. They are very susceptible to collision with the solvent molecules. Therefore, phosphorescence in the solution at room temperature is a rare phenomenon. However, the phosphorescence can observe by decrease the temperature of the sample, whereby decreasing the collision with the solvent molecules. In addition, quenching of the triplet excited state by oxygen is responsible for preventing phosphorescence. Therefore, the solution of the analyte needs to be thoroughly degassed before determination of its phosphorescence. That means if oxygen molecule will be there, so they will undergo collision, and the phenomenon of they will prevent the phenomenon of phosphorescence. So this is about the Jablonski diagram, and this is a long question. Now coming to the fluorescence spectrum. So the fluorescence, because from the Jablonski diagram we have already discussed that the fluorescence arises when electronically excited molecule relaxes back from S1 state to S0 state by accompanying emission of radiation. And again from the figure of the Jablonski diagram, we know that when this radiation relaxation takes place, the molecule can come to any one of the vibrational energy level of S0 state. This implies that the emission radiation is constituted of different wavelength. A plot of the emitted radiation as a function of wavelength for any given excitation wavelength is known as emission fluorescence spectrum, and the figure excitation radiation is shown to have got the transition from S0 to S2 state. So here excitation that is in the figure 5.1, you can see the excitation takes place from S0 to S2, and again internal conversion S2 to S0, S2 to S1, and after that from S1 to any vibrational level of S0, that is called fluorescence. So the emission spectrum would still remain the same because the fluorescence emission generally occur only the first excited singlet state irrespective of the excited singlet state produced initially. And again you will observe in the figure 5.1 that the fluorescence emission remains the same for both the excitation, that is from S0 to S1 or for S0 to S2. However, the intensity of emission would be expected to change because the excitation radiation is absorbed to different extents. Now, if we change the wavelength of the excitation light, plot of emission of the sample to give the emission to give at a given emission wavelength against wavelength of the excited radiation, that result excitation spectrum, and the emission fluorescence and excited spectra of 9-methyl anthracene is given. So this is the fluorescence spectra of 9-methyl anthracene. So from the 9-methyl anthracene you can see, so this is the excitation wavelength, that means the molecule will undergo excitation by absorption of energy within this range, this nano within this wavelength range, and after that again they will come back to the ground state by emitting light or by emitting glow. So the emission spectra having lesser wavelength, so this is the emission spectra. So this is excitation spectra and this is emission spectra. Since a given analyte can fluorescence only after it absorbs the radiation, and excitation spectrum consists of wavelength of light that the analyte is able to absorb. In other words, generally the excited spectrum of a molecule is the same as the UV visible absorption spectrum. Therefore, the excitation spectrum of a compound should not change if you change the emission wavelength that being measured. If thus if the excitation spectrum varies with the choice of emission wavelength, we can say that the observed fluorescence is arising from two or more different substances. This fact may be exploited to check the purity of the fluorescence analyte. Generally, the maximum in the fluorescence spectrum of a compound occurs at a longer wavelength than the maximum in the absorption spectrum. So the wavelength difference between the absorption and fluorescence maxima is called Stokes shift. So this is the absorption maxima and this is emission maxima. So this wavelength difference is known as Stokes shift. Now coming to the which species are fluorescent and phosphorescent. So first coming to photoluminescence and structure. There is no specific requirement for a molecule to make it fluorescent. However, there are certain common observations. For example, the presence of benzene ring and the nature of the substance on it seem to favor the fluorescent behavior of the molecule. So the halogen substituent tends to decrease the fluorescence and shift the fluorescence band to longer wavelength. This effect increases with increase in atomic mass of the substituted halogen. So if a benzene ring will be there in any type of molecule, so that will show fluorescence spectra, and if some halogen substitution will be there, that will tends to decrease the fluorescence and shift the fluorescence wavelength to longer. And and again, if there will be increase in atomic mass of the halogen atom, then the atomic mass of the substituted halogen atom, then the fluorescence spectra will fall still longer wavelength. Now, compound with fused rings are found to be especially fluorescent, and the extent of fluorescence is found to be directly proportional to number of rings in the molecule. Then the structural rigidity of a molecule favor fluorescence. That means in fused ring, the structure will be so rigid inside the molecule, and that will favor observance of fluorescence. For example, fluorescence is a highly fluorescent molecule, while the structurally similar phenolphthalein is essentially non-fluorescent. So here two molecules are there. One is fluorescein and another one is phenolphthalein. So the fluorescein is fluorescent, but the phenolphthalein is non-fluorescent. So why this is happening? In case of the molecule fluorescein, the there will be fused ring structures are there. So one fused position, this is another fused position. So due to this type of fused ring structure, the molecule is rigid and that is susceptible to fluorescence. But in case of phenolphthalein, the rings are not rigid. That means the benzene rings are not rigid. So that's why that is non-fluorescent. The increase in fluorescence The increase in fluorescence is due to lack of collision in the rigid molecules. Another example is biphenyl, which has a low fluorescence quantum efficiency, that is around zero point 0.2, while the fluorine with a rigid structure having a quantum efficiency equals to 1. So this is, you can see, so this is a biphenyl, two benzene rings are there, but the fluorescence quantum yield is only zero point 0.2. But in case of fluorine, although two benzene rings are there, but they are rigid, but they are fused ring structure. So that's why its quantum yield is 1. Its quantum yield is zero point 0.2 for biphenyl, but for fluorine, the quantum yield is 1. And complex formation also leads to the rigidity of the molecule and shows higher fluorescence. So that means if more complex structure will be there, then the molecule will become rigid and that will become fluorescent. For example, 8-hydroxyquinoline, when complexed with zinc ion, increases its fluorescence to a good solvent. So that means, so this is the 8-hydroxyquinoline. This is 8-hydroxyquinoline HNH. 8-hydroxyquinoline is this structure with hydrogen atom. And if the 8-hydroxyquinoline is complexed with zinc ion, so that will give light to this structure and that will become so rigid and that will become fluorescence. The fluorescence observed with rigid cyclic molecules with pi bond is found to enhance the electron donating group. The fluorescence observed with rigid cyclic molecules with pi bonds is found to be enhanced by electron donating groups, that is NH2, OR, OH, OCH3, while the electron withdrawing groups such as COOH, NO2, N double bond N, Br, I, CH2, COH tends to reduce it. On the other hand, the non-rigid molecules do not show fluorescence as these are rapidly lose the absorbed energy through the non-radiative means like relaxation or even degradation. So that means if the molecule is a non-rigid molecule, that will not show any type of fluorescence, the phenomenon of fluorescence, because after the excitation they will come back to the ground state by non-radiative transition. And the substances on the aromatic ring may affect both the intensity and position of the fluorescence band. Another observation is that the simple heterocyclic compounds like pyridine, furan, thiopine, pyrrole do not fluorescence significantly, but when fused with benzene ring, they may become highly fluorescent. So these are pyridine. So pyridine is a non-fluorescent molecule, but when that will fuse with a benzene ring, that will become highly fluorescent. So quinoline and isoquinoline are fluorescent molecules. Despite the above mentioned categories of the molecule, the number of molecules having intrinsic fluorescence capability is very small. However, this does not limit to the application of fluorescence measurement. The applicability of fluorimetry can be extended by derivatizing the compounds do not exhibit intrinsic fluorescence to make fluorescent derivative. Another possibility is the non-fluorescent molecule may be chemically attached with a fluorescent tag or fluorescence level. Now let us understand how the structure of a molecule affects its characteristics of the phosphorescence. So here we have discussed how the structure of a molecule so its fluorescence characteristics. So now we will discuss how the structure of a molecule affect its characteristics of phosphorescence. As the regards of phosphorescence, it has been observed that the introduction of certain paramagnetic metal ions such as copper or nickel gives rise to phosphorescence. So the ions do not induce fluorescence. The contrary to magnesium zinc compounds, so the introduction of magnesium and zinc will show fluorescence, while the introduction of copper and nickel gives rise to phosphorescence. Phosphorescence is affected by molecular structure such as unsubstituted cyclic or polycyclic hydrocarbons and those containing methyl group, NH2 group, OH2 group, carboxylic acid group, OCH3 group substituents which have lifetimes in the range of 5 to 10 seconds for the benzene derivatives and 1 to 4 seconds for the naphthalene derivative. So, if so these groups will be introduced in the benzene derivative, the lifetimes of the phosphorescence will become 5 to 10 seconds. But for naphthalene derivative, so the introduction of these groups in so the lifetime with 1 to 4 seconds. The introduction of nitro groups in a structure diminishes the intensity of phosphorescence as does introduction to aldehyde and ketonic groups. Just like aldehyde and ketonic groups, the introduction of nitro group will diminish the intensity of phosphorescence. The emission lifetime tau in the second in the rigid media and it's around 10 to the power minus 2 to 10 100 second in a fluid media. So now, so here it is given which compounds, so which of the molecules are expected to be fluorescent. We have already discussed that if rigid ring structures are there, the molecules show fluorescence property. So the number 3 is the answer. Now coming to factors affecting fluorescence and phosphorescence. So first one is the temperature. A rise in temperature is almost always accompanied by decrease in fluorescence. The change in temperature also causes the viscosity of the medium to change, which turn changes the number of collision of the molecule of the fluorophore. Fluorophore means the molecules which will show the fluorescence property, that is known as fluorophore with solvent molecules. So the increase in the number of collision between the molecules in turn increase the probability of deactivation by internal conversion and vibrational relaxation. So in such cases, it is recommended to use thermostated cell holders. So that means if temperature will be increased, the molecules will undergo collision and the molecules will undergo collision more rapidly. So they will lose their energy from the excited state by different non-radiative processes. That means by different internal combustion process or by vibrational relaxation processes. So that's why its their fluorescence intensity will decrease. Now coming to the next factor, pH. Relatively small changes in the pH can sometimes cause substantial changes in the fluorescence intensity and spectral characteristics of fluorescent molecules. For example, so one molecule serotonin shows a shift in the fluorescence emission maximum so for the molecule serotonin, it will show a fluorescence emission at neutral pH level 330 nanometer, and if the medium will become strongly acidic, its fluorescence emission wavelength, fluorescence emission maximum will shift from 330 nanometer at neutral pH level to 550 nanometer in strongly acidic without change in absorption spectrum. Now coming to dissolved oxygen. The paramagnetic substances like dissolved oxygen or many transition metals with unpaired electrons dramatically decrease the fluorescence and cause interference in fluorometric determination. So the paramagnetic nature of the molecular oxygen promote intersystem crossing process, and that's why the fluorescence intensity will decrease. Now coming to solvent. The change in polarity or hydrogen bonding ability of the solvent may also significantly affect the fluorescence behavior of any analyte. The difference in the effect of the solvent fluorescence is attributed to difference in their ability to stability in the ground and excited state of the fluorescent molecule. This alters the probability of energy of both the absorption and emission bands. Now coming to fluorescence quenching. So the fluorescence emission is quite sensitive in the presence of impurities and other species. So if impurity, other species like paramagnetic oxygen molecule or any metals which contains lone pair of electrons, so they will decrease the fluorescence intensity. This caused a decrease in intensity of the fluorescence emission. So these decrease in the fluorescence intensity arising out of interaction with excited state of the fluorophore. Fluorophore means the molecule which will show fluorescence. So there is a decrease in fluorescence intensity arising out of the interaction of the excited state of the fluorophore with the surrounding, that is called quenching. That means the phenomenon by which the fluorescence intensity will decrease by interaction with other molecules, that is called quenching. For example, quinine fluorescence is quenched by the presence of halide ion. So if halide ion will be there in the solution, the quinine molecules, the fluorescence intensity of the quinine molecule will be decreased and that will undergo quenching. One of the mechanism of the quenching involves the collision between the excited and ground state of the molecules, leading to increase in amount of the radiation-less relaxation. It is called self-quenching. So that means if same molecule will undergo collision with one another, then there is also increase in the amount of radiation-less process, and that's why the fluorescence intensity will decrease. That is called self-quenching. It alters the ratio of the excited molecules that relax via the fluorescence pathway. Since the self-quenching depends upon the rate at which the collision occurs, it increases with an increase in concentration of the analyte. So that means if the concentration of the analyte will be increased, the degree of self-quenching will increase, and hence the intensity of the fluorescence will decrease. Due to the self-quenching, the photoluminescence efficiency varies with concentration. Another mechanism that leads to the fluorescence intensity, that leads to the decrease in fluorescence intensity, that means decrease in fluorescence intensity is called quenching. And here another mechanism that leads to the decrease in fluorescence intensity is called self absorption or inner cell effect. It is observed it is observed in the molecule in which the absorption band overlap with the wavelength of the emitted photon. And in such a situation, some emitted photons are reabsorbed before they can escape from the solution. This is called self-absorption, and similar to self-quenching, this is also significant at high analyte concentration. So this type of self-absorption or inner cell effect type of quenching will be observed if the concentration of the analyte will be high. A significant portion of the excitation radiation is absorbed by the sample before it reaches the center of the cuvette. As self-absorption is a physical artifact, so the principle can be eliminated by proper cell design and measurement of condition. Now, the intermolecular electronic energy transfer from excited molecule to the quencher molecule is one of the common ways by which the fluorescence quenching occurs. The process can be represented by, suppose this is the excited molecule, and if the excited molecule will react with some any other species, that is called a quencher, and hence the excited molecule come back to the ground state by radiation-less process, that is called quenching. If the excited molecule come back to the ground state by emission of light immediately, that is called fluorescence. So due to presence of this quencher, the fluorescence intensity decreases. When the excited analyte molecule transfers its energy to the quencher molecule, thereby gets de-excited to M, forming an excited quencher molecule, Q star. In case of Q star happens to be fluorescent species, then its fluorescence is called sensitized fluorescence. So the sensitization of fluorescence can one way to observe fluorescence from a molecule Q to that otherwise difficult to excite directly. So the quenchers are generally not desirable for the fluorimetry determination. Mathematically, the quenching follows Stern-Volmer equation. So this is another long question, that is called Stern-Volmer equation. And the equation can be given as phi f naught divided by phi f equals to 1 plus ksv. So here phi f naught and phi f are the fluorescence quantum yields for the analyte in the absence or presence of quencher respectively. So that means phi f naught is the quantum yield of the analyte. Phi f naught is the fluorescence quantum yield of the analyte in absence of quencher, and phi f is the fluorescence quantum yield of the analyte in the presence of quencher. And here KSP is nothing but quenching constant. In an alternate mechanism of quenching, the quencher molecule form a complex with analyte molecule, which is then deactivates using some internal conversion mechanism, and the mechanism can be represented as follows. So here this is the excited molecule react with quencher, and that will form a complex, and after that that will undergo radiationless process. So here the in this mechanism of quenching, the quencher molecule form a complex with the analyte molecule which is already excited, and when then deactivate using some internal conversion mechanism. So here the quencher molecule form a complex with the excited molecule, that is A star. So Q form a complex with A star. After that, that will become AQ star, and after that the AQ star converted into AQ by internal conversion mechanism. That means by radiation less process. This is also one type of quenching process. In this mechanism, the effect of concentration of the quencher molecule or the analyte can be understood in terms of simple law of mass action. A higher concentration or any by a simple law of mass action, a higher concentration of any of the two shifts the equilibrium to the right, and analyte fluorescence is quenched to a greater extent. So that means higher concentration of the analyte or higher concentration of the quencher leads to the process, leads to shift the equilibrium towards the right hand side, that is the process of quenching. Now coming to quantum yield. So a number of processes contribute toward the deactivation of the excited state. Only a certain fraction of the excited molecule relax through the fluorescence pathway by emission of radiation. This fraction, quantified in terms of a parameter that is called quantum efficiency or quantum yield. Mathematically, quantum yield, that is phi, equals to number of emitted photons divided by number of observed photons. Number of observed photons will help the molecule for excitation from down to excited state, and from the excited state they will come back to the ground state by different processes, by radiationless process or by radiation process. If they will come back to by radiation process, by radiative process, that is called fluorescence. So that means the number of emitted photons will be less than the number of observed photons in general case. So that means the quantum yield is always less than equals to 1. If the quantum yield will be 1, that is 100% fluorescence. The quantum yield refers to the contribution of the fluorescence to the various deactivation processes of an excited state. The quantum yield is so related to absorption property of a molecule as well as fluorescence lifetime tau. So here phi is also equals to tau by tau naught. Here tau and tau naught are the fluorescence lifetime in presence and in the absence of non-radiative processes. Therefore, non-radiative processes respectively. With the transition rates Kf for the fluorescence, Kic for the internal conversion, Kisc for the intersystem crossing, Kq is the transition rates for fluorescence quenching by quencher molecules, and hence phi equals to Kf divided by Kf plus Kic plus Kisc plus Kq. Now the instrument for fluorescence measurement. So the first one is light source. A fluorescence instrument is usually having same component that is used for absorption spectrophotometer. However, the geometric arrangement of the component is somewhat different. This is due to the reason that the transmitted radiation is not measured along with fluorescence. This is due to the reason that any transmitted radiation is not measured along with fluorescence. You know that the absorption and transition radiant energy occurs only along the direction of the incident, where in case of fluorescence radiation occurs in all directions. So the detection of transmitted radiation is avoided by placing a detector at a right angle to the transmitted beam. So this is the light source. This is observance. So that will show observance, absorption spectra, and this is detector. After that, the molecule will come back to the S1 state, and then from the S1 state that will come back to the S0 state by the process of fluorescence. So that is the detector. So the essential component of an instrument to measure the fluorescence is excited light source, then filter or monochromator, then sample holder, then detector, then the output devices. So these are the different light source. So the instrument of fluorescence. Now coming to the instrument for phosphorescence. So you know the basic difference between the fluorescence and phosphorescence is that the phosphorescence emission occurs at different time frame and can be measured only if the sample is solid or at liquid nitrogen temperature. That means only if the sample is solid or it at liquid nitrogen temperature. That means at very low temperature. Therefore, the basic instrument phosphor, for phosphorescence is similar to that of the fluorescence. However, two aspects of measurement need to be modified. The first is the sampling technique, and the second being the recording procedure. So here the sampling technique. So in the sampling technique, the sample will show fluorescence at liquid nitrogen temperature. So that's why this is the sample tube that is surrounded with liquid nitrogen. That is at 77 Kelvin. Now application of fluorescence and phosphorescence molecules. So fluorescence spectroscopy and its application to the physical and life science have been rapidly during past decade. It is widely used for the qualitative and quantitative analysis of inorganic compounds and has become extensively used for the spectroscopy techniques in the field of biochemistry and molecular biophysics also. Despite the fact that the fluorescence measurement do not provide detailed structural information, the technique has become quite popular in this area. This is due to the sensitivity to change the structural and dynamic properties of the biomolecules and biomolecular complexes. The increased in, the, the increased interest of fluorescence appeared due to the advanced time resolution. In case of inorganic analyte, though these are fluorescence or phosphorescence in the solid state, majorly of analysis work undertaken in solution state. For the purpose of fluorimetric analysis of inorganic analyte and inorganic analytes, either in direct or indirect method used, you know that in the direct method, the native fluorescence of the analyte is used, where in case of indirect method, the analyte is converted into fluorophore by making a complex with suitable organic compound. So that means if the molecule will be directly initially fluorophore, then that can be measured by direct analysis. And if the molecule will not fluorophore, then you have to form a complex with suitable organic compound so that the molecule will initially become fluorophore, and after that you have to measure the fluorescence spectra. And here are some common application of fluorescence. So that is if the compound vitamin A, the fluorescence emission occur at 500 nanometer, that is application for foodstuff, vitamin tablets, etc. And these are other examples are there. And after that we will move to the next chapter. You see, the next chapter is application of fluorimetry and phosphorometry. First one is fluorescence analysis method. So here we will discuss direct analysis method and indirect analysis method. In the direct analysis method, we measure natural fluorescence of the analyte. A few inorganic species fall under this category. That means the molecule should be naturally fluorescent. Whereas the number of organic species in this category is quite large. A few inorganic species fall in this category, but number of organic species for this category is quite large. In this category of inorganic species of lanthanides, cerium and europium being the most common example. So that means inorganic complexes of lanthanides like cerium and europium complexes are more common example, and similarly complexes of actinides like uranium are most important, and some other like thallium also reasonably intrinsic fluorescence property. And now coming to indirect analysis method. So in the indirect analysis method, the fluorescence is not measured directly. There are two strategies for the indirect analysis method. In the first strategy, for the analyte to be determined suitably is derivatized by a fluorescence species. So that means initially the analyte will not show fluorescence property. Initially you have to convert this analyte into fluorescent molecule by derivatized to a fluorescent species. For example, 2-hydroxybenzaldehyde, that is salicylaldehyde, form a bond with metal and the resulting species become fluorescent. So this is salicylaldehyde. So this is a non-fluorescent molecule, and if that will complex with a metal, so that will become salicylaldehyde bonded with a metal, and this one will become fluorescent. After that, you have to measure the fluorescence property. And then fluorescence spectroscopy in quantitative analysis. So for quantitative analysis, so that is concentration dependence of fluorescence, a spectrometer, a spectrometer method can be put quantitative analytical application only if the spectral characteristics like position, intensity with the spectral band can be related to the concentration of the analyte. Let us establish a relationship between the fluorescence intensity and concentration of the analyte. And you again we know that QF, that is fluorescence quantum efficiency or quantum yield, equals to number of photons emitted by number of photons absorbed, which is also equivalent to intensity of fluorescence divided by intensity of absorption. That is QF equals to PF by PA. PF is nothing but intensity of fluorescence and PA is intensity of absorption. On rearranging the equation, we can write PF equals to QF PA, or PA equals to P naught minus PT, because PA is the intensity of absorption and P naught equals to the intensity of the radiant power, and PT is the radiation power of emission spectra. So that means this much of this intensity of light will be observed. So this is initial incident radiation intensity of the incident radiation, and this is intensity of the radiant power emission spectra, and that's why the intensity of the absorption PA equals to P naught minus PT, and hence we can write PF equals to QF whole into P naught minus PT, or which is equals to QF P naught whole into 1 minus PT by P naught. And again we know that PT equals to, and again we know that PT equals to P naught into e to the power minus epsilon BC, and which implies that PF equals to phi t into P naught whole into 1 minus e to the power minus epsilon BC. And again we know that by expansion series we know that e to the power minus x equals to this much. Putting this value, we can find out that PF equals to phi f P naught epsilon BC. So that means the PF is directly proportional to concentration. So thus the fluorescence intensity of the sample can be used for the concentration determination of the analyte. Now coming to factors affecting quantitative application of fluorimetry. So the quantitative application of fluorimetry can be affected due to presence of self-quenching, radiant energy absorption, self-absorption, and interfering species. So these are the species which will change the intensity of fluorescence spectra. Now coming to fluorimetry and environmental monitoring. So This spectroscopy method can also help for the analysis of gaseous pollutant. The analysis of gaseous pollutant is based phenomenon of the chemiluminescence. We begin with the determination of NO, NO2 as atmospheric pollutant. So the first one is determination of NO, NO2. In order to determine the amount of NO, the gas is passed through a reactor in which it will react with ozone and initially excited to NO2 star species which produce for the reaction as per the reaction given below. So NO react with ozone to form NO2 excited molecule plus O2. So the activated NO2 then gives chemiluminescence broadband with the visible IR range and revert back to a longer energy state. So the emitted photons proportional to the amount of NO present in the substance, which helps with the help of a photomultiplier tube. So the concentration of NO2 star is also directly proportional to concentration of NO present in the air. So that's why by this technique we can measure the presence of NO in the air. So this is the schematic layout for the determination of NO2 chemiluminescence by chemiluminescence method. Now determination of SO2. So these are the various chemical methods. By the application of fluorescence, we can measure the concentration of this type of air pollutant present in our air. So these are the techniques, environmental pollution remediation techniques. And then the fluorescence spectroscopy in medicine and biology. So analysis of amino acid and proteins, then fluorimetric determination of blood glucose. The amount of blood glucose can also be determined fluorimetric method. Then analysis of blood serum, analysis of calcium ion, etc. So these are the application of fluorimetry for medical application. Fluorimetric analysis of inorganic substances. After that, the fluorimetric analysis of inorganic substances. So, in order to know the concentration of any type of inorganic substances, first you have to make the molecule to be fluorescent by formation of suitable complexes, and after that we will measure the fluorescence intensity. From the fluorescence intensity, we can determine the concentration of the complex, which is directly proportional to concentration of inorganic sample present in the analyte. So by this method, we can also measure the concentration of the inorganic species. So these are few other applications, and again phosphorometric method in chemical analysis, but it has very less application. So now we will discuss the next chapter. The next chapter is flame photometry. Flame photometry. So first one is origin and classification of atomic spectroscopic method. So the flame photometry is completely associated with atomic spectroscopy. So first one is origin of atomic spectrum. An atom contains a set of quantized energy levels that we have already known that in atom the different quantized energy levels are there, K, L, M, etc. And that can be occupied by the electrons depending upon the energy. The energy levels with minimum energy is called ground state, while that one with higher energy are referred to as the excited state. Further, the electrons in an energy level can undergo transition to another level of a higher energy by absorbing a photon of appropriate energy equals to the difference of the energy of the two levels. One, on the other hand, the transition of an electron from a higher energy level to a level of lower energy is accompanied by emission of the different energy in the form of a radiation of appropriate wavelength. A spread of the wavelength of the photons absorbed or emitted versus their intensity is called a spectrum. So the atomic spectroscopy methods are based on transition among the quantized electronic energy levels caused by absorption of radiation by the atoms in the ground state or by emission of radiation by excited atom in the vapor state. Now classification of atomic spectroscopic methods. So here we have studied that we know that the electrons are present in different quantized energy levels in an atom. So the energy level with minimum energy is called ground state, while that of energy level with with higher energy, that of the ground state, that is known as the excited state. And again, the electrons in the energy level can undergo transition from ground state to any one of the excited state by absorbing appropriate amount of energy, which is equal to the energy difference between the ground state and the excited state. So if the electron will absorb energy by the energy difference between the ground and the excited state, then the electron will move from ground state to the excited state. So that is called absorption spectrum. And again, from the excited state, the electrons coming back to the ground state or the lower energy level directly or indirectly, that is called emission spectrum. So the classification of different atomic spectroscopic methods, different atomic spectroscopic methods are there. First one is flame. So first one here we will discuss the flame photometry. So this is one type of atomic spectroscopic method. Then electrothermal method. Then ICP, inductively coupled argon plasma method. Then direct current argon plasma method. Then electric arc method. So these methods accompanied with atomization processes in different temperature ranges. Once in the vapor phase, the atoms of the element interact with the radiation and provide information about themselves. So the interaction of radiation of the matter can manifest itself in terms of absorption, emission, or fluorescence emission. Accordingly, we have atomic absorption, emission, or fluorescence spectroscopy. Now let us learn the basic principle of these methods. So first we'll discuss what are the basic principles. So the first one is atomic absorption spectroscopy, AAS. So in this method, the atomic vapors containing free atoms of the element in the ground state are subjected to a UV visible radiation, which is a characteristic frequency of the element present in the atomic vapors. The radiation is absorbed and the intensity of the radiation is attenuated. The absorbed radiation causes excitation of electrons from the ground state to the excited level. The extent of absorption is quantitative measure. The extent of absorption is a quantitative measurement of concentration of the atomic vapors of the element in the ground state. This can be, so it is an electronic excitation and the energy of the transition lies in the UV visible region of the electromagnetic spectrum. So this is called AS. So that means in the AS, the atoms should be present in vapor form, that is free atom, isolated gaseous atom should be there, and after that the isolated or free atoms in the free atoms in the vapor state will be irradiated. The free atoms in the vapor state will be irradiated with electromagnetic radiation in the UV visible range, so that the electrons present in the ground state of the different atoms, they will go to the excited state and they will show the excitation absorption spectra, and from the intensity of the absorption spectra we can find out the concentration of the atoms present. So that is called AAS. Now coming to atomic emission spectrometer. So in this method, a sample is normally excited by thermal energy of a flame, argon plasma, or an electric discharge. The atom in the sample absorbs thermal energy, causing the excitation of the outer orbital electron. Again, so repeating this, a sample is normally excited by thermal energy or by a flame. So that means the sample in the atoms in the vapor state will be normally excited by flame or thermal energy, and or that is excited by thermal energy like a flame, either a flame or argon plasma or electric discharge. The atoms in the sample absorb thermal energy, causing excitation of the outer orbital electrons. As the excited state is short-lived, they will come back to the ground state after a very short time, typically around 10 to the power minus 6 to 10 to the power minus 9 seconds. This is accompanied by emission of electromagnetic radiation, normally fall in the UV visible region, and the wavelength of the emitted radiation is the intense, and its intensity provides the qualitative and quantitative information about the atoms present in the analyte. The atomic emission spectroscopy employing flame is known as flame photometry or flame emission spectroscopy. So, if the atomic emission spectroscopy will take place by flame, that is called flame photometry or flame emission spectroscopy. And similarly, the atomic emission spectroscopy may also take place by argon plasma, or that may also take place by electric discharge. Now coming to atomic fluorescence spectroscopy. So in the atomic fluorescence AFS, the gaseous atoms are excited to higher energy level by absorption of electromagnetic radiation and the fluorescence emission, and they causes fluorescence emission from these excited atom is measured, and they causes fluorescence emission, and the fluorescence emission of this excited atom is measured, and the main advantages of the fluorescence detection compared to the absorption measurement is greatly sensitive, achievable because of the fluorescence signal has a very low background radiation and so here a schematic representation of the transition phenomenon associated with atomic absorption, atomic emission and atomic fluorescence. So this one is atomic absorption. So the electron present in the ground state of the atom, by absorption of energy, they will move from ground to excited state. So that is called atomic absorption spectrum. And from the excited state, if they will deactivate to the ground state by emitting photon, that is called atomic emission spectrum. And from the excited state, if that will deactivate to the ground state by emitting light, that is called fluorescence. And similarly, non-resonance fluorescence. So this is called resonance fluorescence and this is called non-resonance fluorescence. For the resonance fluorescence, so if that will directly come back to the ground state by emitting light, that is called resonance fluorescence, and if that will indirectly come back, that is called non-resonance fluorescence, that will discuss in details later. Now, so the basic the basic principle of these phenomena are the atoms should be free from one another or isolated from one another. So we have a number of method of atomization, that is absorption, emission and fluorescence emission for measuring radiation of measuring so radiation analyte interaction. There are number of different types of atomic spectroscopic methods. So the types of atomic spectroscopic method is determined both by the method of atomization as well as the nature of interaction. So that means first atomization should be there. For example, an atomic spectroscopic method using electrothermal atomization method and studying the fluorescence emission spectroscopy, that is called electrothermal atomic fluorescence spectroscopy. And similarly, different types of atomic spectroscopic methods are there. So the different atomic spectroscopic methods that will discuss tomorrow. Hello, hello.
Okay, sir.
Okay.
आज तो जल्दी खत्म होगी क्लास।
हाँ, क्या हुआ सर को?
पता नहीं।
ऐसे जल्दी जल्दी में चले गए।
अरे कोई बच्चे आ ही नहीं रहे।
अरे यार, हाँ
दिक्कत तो यहाँ
वो भी सही, वो भी
सामने
सही
कोई
है।
बच्चे दिखेंगे तो पढ़ाएंगे भी।
ये पढ़ा भी रहे हैं, मतलब गा जा रहे हैं।
हाँ वो गाए जा रहे हैं बस।
वही तो। और दो चार होते तो क्वेश्चन वगैरह पूछते तो ये अच्छा रहता।
हम्म।
हम्म,
चलो ठीक है फिर हाँ।
ठीक है।